Hello everybody, welcome to our game theory seminar, the seminar of the Moroccan Center for Game Theory. Today we have the big pleasure to have Yann Chevalleyre, who was my colleague at Dauphine University. This week he is teaching at the PhD program, a course, very interesting course on how to use game theory to construct robust to attack algorithms in machine learning. So I know Yann for many years now. When I came to LAMSAD, it was in 2013, so 12 years ago. It was very quick. And we had the pleasure to have at least one PhD student together, but we did other collaborations, and hopefully with this new experience and new cycle of our collaboration, we will have lots of other PhD students and collaborations. And Yann is doing a very nice and great talk, complementary to all the talk we had before at the center. So now with the really modern AI, deep learning, and modern algorithms, and in particular this question how to construct robust algorithms, and I think that his talk today is related to the topic of his lecture. So Yann, it's your floor, and thank you for coming to Morocco and visiting us and helping this center to develop.
Thank you very much, Rida. It's an honor for me to be here, and so thank you very much for having invited me for this week. So the title of my talk is Robustness in Machine Learning, Randomization in the Multiclass Setting. So in fact, I'll talk mainly about the biclass setting, and the last quarter of an hour will be about the multiclass setting. So it's not really relevant. Okay. So let's start. Context and motivation. So as you all know, machine learning and deep learning have been extremely successful in so many applications, and they have beginning to be used in critical applications such as personal devices for decision making or for AI-driven technology like autonomous driving and lots of other domains like these ones. So despite their very good results, they are in the real world. In fact, there are lots of issues when you deploy machine learning algorithms in the real world. The biggest issue is the robustness. In fact, the performance of machine learning algorithm can really degrade very quickly, either under adversarial attack, either under distributional shift. So adversarial attack is when there's an attacker which intentionally changes a part of your data at inference, and distributional shift is when you train data on a particular distribution, but then when you deploy it, for example, you train a classifier for healthcare in France and you deploy it in Germany, so the population is not exactly the same, so performance might degrade. So this is about robustness. Other big issues like, for example, fairness, where you don't want to you want to be as nice to every demographic group wherever they are. Other very important issues are privacy and performative learning. So privacy, you want to protect data. We saw currently that for example, in large language models, there were big problems of privacy because the large language models memorized a huge part of their training data, so it could memorize sensitive information, which was not very good. So privacy is an issue, and performative learning is also a big issue. Performative learning is when the way you deploy the model in the nature, in the real world, will affect people, and they will react to this, and things might go wrong. But you have to anticipate this. Okay, so lots of these can be formulated. So this is a bit of provocative writing, because it's not necessarily exactly a zero-sum game, but most of them can be seen at least as a game. So robustness, group fairness, privacy, performative learning. So robustness, it's obvious because you have an adversary Well, group fairness, you have to be fair among all groups. So the worst group should be as well treated as possible. So in some way, you can imagine there's an adversary selecting a bad group. This could be a way to see it as a zero-sum game. Privacy also, there are what we call privacy attacks, where people try to deliberately extract private information from models. So it could also be seen as a zero-sum game, and performative learning is a field where we search for an equilibrium, which might be formulated also as a game. Okay, so three persons who contributed a lot to this presentation, in particular Luc Agnico, on which Luc Agnico and Laurent, on which lots of what I'm presenting is based. So these were PhD students. Luca is still in PhD with me. Okay, so let's dive into the topic. So I'll talk about supervised learning. So robustness is also relevant in generative AI and lots of other topics in AI, but in supervised learning, it's the simplest case. So let's say we have ground truth distribution, which explains the links between images and categories, cat and dog. So you have the set of images, which is big X in RD. You have the set of labels, which is, for example, -1, 1, referring to dogs or cats. And you have a data set, which is drawn from a distribution, which is unknown, which is D. And you want to understand the link between the images and the label. So the goal is to use this distribution to design a mapping H, mapping images to labels, which should match as best as possible the relation from X to Y present in the distribution, which is unknown. So to handle this, you have to define a loss function, which evaluates how well your prediction do, and you want to find a classifier, a function H, which among a big class of function, which minimizes the risk. So the risk would be, for example, the error probability that your model does on the distribution P. Okay, so of course we don't have access to the distribution D. So D, we can write it down as the sum of the distribution over for label 1, which is D-1, and for label D1 and D-1, which is P of X given label is 1 and P of X given label is -1. So the usual way to represent it is two Gaussian representing the distribution of label 1, label -1. And if you pick the best classifier, which is here just to cut in the middle and to classify this as 1 and this as -1, you will endure this error. So this error is simply, it's classical in statistics, is the sum of type 1 error and type 2 errors. So if you integrate this area in gray, it represents the probability of misclassifying an example based on using this classifier here. Right. So recall that we only have access to training samples, x1, y1 to xn, yn. And usually the only thing we can do is to try to find H which minimizes the empirical risk rather than true risk. And of course, we hope that with more data, the empirical risk converges towards the true risk, which is not always the case. Okay, so we work usually with neural networks. So neural networks is a family of function which is basically compositions of functions. So each function is a composition of as many functions as there are layers in your network. Okay, so you put an image at the input of the network, and it outputs, for example, labels. So we won't go deep inside what neural networks are, but you can have deep convolution networks. There are still lacks theoretical guarantee, although the domain is really very, very quickly growing. Theoretical guarantees on neural networks, very, very quickly. And they are extremely vulnerable to malicious data manipulation. So should I... D'accord, je touche à rien. So adversarial attack, which is the topic of this talk, is already an old subject. Because of course machine learning, for machine learners, anything older than 5 years old is already very old. So an adversarial attack is basically a perturbation that you add to your input. So if your input is an image, the perturbation is itself an image, a very, very small perturbation, so that the resulting image you get is completely indiscernible by a human from the original image, but from the point of view of the neural network, it's no more the same, it should no more be classified as the same level. So, for example, this image was cat, and with this perturbation, it becomes a dog. Okay, so the notion of imperceptibility we often use is a norm. So we allow a perturbation tau, which is for a p norm lower than epsilon. So there are lots and lots of attacks which exist. Attacks are very, unfortunately, very easy to design for most models. So there are huge security issues. For example, recognition on smartphone or autonomous driving vehicles, which is really a big one. Okay, so from the adversary's point of view, the adversary, which is attacking your model by changing a little bit of pixels in your image when you're using it inference to classify your image. His goal is to find a perturbation tau inside the ball of radius epsilon, which maximizes your loss. He wants to fool you. So, for example, what could an attacker do on this two-Gaussian problem? He could pick all the examples of class -1, all of them, and what would perturbation be which would really increase the loss? It would be to move all of them to the right. So to the right by an amount of epsilon. So if you do this, you can look up. The d-1 has shifted to the right. And now, unfortunately, you incur a new loss. All right? This area in purple represents the new amount of loss that the adversary has caused you. Okay? Okay, so attacks often are based on gradients. So the gradients of the loss, which is a reasonable thing to do. The gradient is the direction of the biggest increase. So if you want to change an example, an input of a neural network to increase its loss, you should probably go in the direction of the gradients. Okay, so most attacks are based on various gradient ascent techniques, or most of them. So for example, there's the fast gradient method, projection gradient method, and attacking every point in a data set with a very small radius makes the accuracy drop to 0%. So it's really critical. Okay, so what about the adversarial risk? Right, so our goal is to find a classifier H which minimizes the adversarial risk, as you see here. So let me detail this risk again. This is the expectation because we are going to average the loss over all Chinese examples weighted by their probability. And for each example, the omniscient adversary is able to compute a perturbation, a small perturbation, to increase the loss himself. So there's a natural zero-sum game formulation because we're trying to minimize this. So we'll formalize this game and study some of its properties. So this game can be formulated as inf sup. So let me go back a little bit. Right now, it's not exactly an inf sup. Okay, see, if I'm trying to find the best classifier, I would type inf on H of the expectation of a sup. So we'll see how we change this in an inf sup. So trust me, for now, we can look at this. So looking at this at a game, if we wanted to study, for example, the Nash equilibrium of game, we would have to look if the best response of the classifier player to a certain kind of attack is stable, is the same as at himself, or what is the best response of the classifier to some attack, and what is the best response of the attacker to some classifier. And of course, we would have a Nash if there would be a pair, which would be a stable state, which is one classifier and one attacking strategy, okay, which would belong to the best responses of one another. All right. So you saw that I used function phi to define the attacking strategy. So let's detail what I mean by there. So the classifiers, which are the classifiers, the family of classifiers I'll be using is big H, family of functions from X to R, on which I compute a loss. And then I assume that the attacker, the strategy of the attacker is modeled by a function phi, and of course phi belongs to big F, which is all the strategies he can adopt. So phi is a transport plan, basically, because phi is a function moving a point X to another point X prime, such that the distance between X and its transported version is bounded by epsilon under the P norm. Okay, so phi is the transport function. Okay, so this was the adversarial risk, the standard adversarial risk, which you can decompose in expectation of a y, expectation of a x given y, and same thing inside the expectation. So in fact, the supremum of tau here, in fact, tau depends on x, of course. So the tau which depends on x is in fact a hidden function, which we make explicit here, which we call phi. So phi is the strategy, is the attacking function for a given class y. Okay, so the strategy of the attacker phi is then used to transport the distribution dy. So that's at the end we only have to write the zero-run loss of h of x y. Okay, so this is the push forward where all points from this distribution has been moved by the attacker. So we can write this down this way. Okay. Okay, so everyone has perfect information, and the adversary has no limitation. He knows everything. So here is basically now the inf sup proper way to write this down. The infimum over h, the supremum over pairs of attacks, because there's the attacking strategy for class 1 and the attacking strategy for class -1, okay, for dogs and for cats. And once you have this, this is the, let's say, the score. So, as we saw earlier, attacking this class, the best way probably to do this is just to move this class to the right and same to the left. But if we do this, before attack, the classifier was this one, the best optimal classifier. And after attack, it stays the same, obviously, with the Niemann-Persson lemma, which we would use to find the optimal classifier, for example. We would find exactly the same. So here the classifier is stable after attack. It's just the risk has jumped by a high amount. Okay, so this is a trivial Nash equilibrium in this case. And there's a very high adversarial risk for Gaussian, low for separable distribution. So it looks like the problem is solved. Just there's a very simple Nash, nothing more to say. But in fact, this case is not realistic. It's not realistic. Why? Because if you look at the movements we made, the transport we made, well, we transported these points over the boundary. So on these points, the attacker won. The attacker made us badly classified all these blue points which are here. But these ones, they were moved for free, okay? So we can imagine that an attacker has a cost to attack. He can't attack absolutely everything, every image. He could at least only attack those on which he would make the classifier fail. So if we add this constraint, we can add this constraint simply by adding some kind of regularizer, and this regularizer only says don't move images, don't move examples if it won't give you a bonus, if it won't increase your score, right? So, under this, there's no more pure Nash equilibrium here. So the proof is involved, but graphically it's quite simple. So if an attacker wants to attack these two Gaussians, he won't move all these points. He moves only the points which he has the budget to make them cross the boundary. So these ones and these ones, right? So this the blue part of the Gaussian has been moved here, and the red which was here has been moved here, right? So this is the attack. Now let's see how the classifier reacts. The classifier reacts by changing the class of these area, because now there used to be red points here, now there are blue points because of the attacker. So how does the attacker react? Well, the attacker can, for example, take all these red points here and send them on this blue area here, and again and again. So in fact, this is not, in this more realistic setting, there's no pure Nash equilibrium. So the sup inv is lower than the inv sup for, there's a duality gap. Okay. Oh, so what happens if we used mixed Nash equilibrium? If we study mixed Nash equilibrium, if the defender uses mixed strategies, randomized strategies, which are, for example, mixtures of classifiers. All right, so let's see a very simple example. So here we have a distribution with 3 directs, 2 red and 1 blue, or 1 blue which has a double weight. So we have 2 classifiers. Let's say our family of classifiers is only this one, F1 and F2. Okay, so here the risk we observe, so F1 classifies this one correctly because it predicts red. It predicts blue everywhere here, so the risk here is 1 out of 4. There's 1 example which is badly classified. And here it is of 1 out of 4 also. Okay, so now let's authorize attacks of the radius sufficient so that these can cross the border. What will an attacker do? He will take the big blue and exchange it here, and the red and exchange it here. And the error climbs to 100%. The risk falls down to 0. Okay, so with these attacks, the resulting risk is 100%, absolutely no well-classified points. But in retrospect, if we randomize here, for example, if we take the F1 and F2 with probability 1/2, 1/2, it means that the center will be classified blue always, but the borders will be classified half red, half blue by just flipping coins for each example. So if we look at what an attacker might do here, well, the red ones, he can attack them to put them in the blue region. He wins. But the blue one, he can attack it by moving it to the right or to the left. He'll always classify it. It will always be classified well 1/2 of the time. So it's not great. There's only 25% accuracy or 75% risk, but it's better than the deterministic version. So this very simple example shows that randomized strategies to defend against adversarial attacks work. Okay? They are necessary, yes, they are necessary. Okay, so let's consider a family of classifier H parameterized by theta. So we're going to go a little bit deeper in randomized strategies. So let's first define a set of classifiers, so parameterized by theta over big theta. And we can define distribution over theta. So if we define distribution over theta, it induces a randomized classifier, okay? So a randomized classifier defined by mu is a classifier you'll pick randomly according to the distribution mu over parameter theta. Each time you have to classify an example. So the loss is the usual loss. So we can now redefine our adversarial risk. Well, not so many modifications. The only modification we have to do is to put an expectation here. Because of course now we have a mixture of classifier, we have a randomized classifier, so we have to take the expectation of the loss, right? So, okay, so, we have this, so we have this minimization problem, whose value we call V rand epsilon, and we can compare it to the deterministic one, where we choose theta inside the class theta. So either we choose a deterministic classifier, standard classifier, either we choose a randomized one, and we look at the performance V rand. Right, so of course, if the radius of attack is 0, then both coincide, okay? Because the soup doesn't make sense if there's no soup if epsilon is 0. So they coincide. And if you allow randomization, you get if you have randomized classifiers under attack, of course you're a little bit worse than if you have no attacks, but you're a little bit better than if you have deterministic classifiers. Okay, so to go a bit further in the formulation, we can define adversarial distribution. So it makes the link between lots of things like optimal transport, like distribution and robust optimization. So let's have a look at this definition. This definition basically is the set of all distribution that can be obtained by considering the transportation of your initial distribution by an adversary. Okay, so there's an adversary which is able to transport any point x to x prime, given that they are far apart by epsilon at most. And so if there exists a coupling on labeled example xy, mapping xy to x prime, y prime at a distance less of epsilon, then the resulting distribution Q is in this set of adversarial distributions. Okay, so A epsilon is in some sense a Wasserstein uncertainty set. We sometimes call it the Wasserstein infinite ball because it's a Wasserstein infinite distance on D. So in fact, it's A epsilon is the set of all distribution who have a Wasserstein infinite distance from D of at most epsilon. Okay, so it's also a convex compact set. So the good point is everything we've done can be formulated with this formalism. So the supremum here can be drawn outside. So we see that the adversarial risk is the natural risk. This is the standard risk, but on which distribution? On the distribution attacked, on the transported distribution, transported by the adversary in A epsilon. Okay? All right. So we defined here, if we look at what we defined up to now, so we defined a randomized defender, a randomized epsilon, and with this adversarial set, we also, let's go back, this adversarial set represents in some way a randomized attacker, okay? But the equality between these two lines shows that for a fixed classifier, the deterministic adversary is just as powerful as the randomized one, which is usual in game theory. All right. So in fact, it's a randomized attacker because this guy, if D is a Dirac, this guy can diffuse a Dirac in many directions inside the ball, for example. But he doesn't have an incentive to do so. All right. So once we have this, we can write the primal and the dual formulation, both being randomized. So inf sup and sup inf. Okay, so the classifier objective is being robust to every attack, and the attacker objective is finding attacks which fool any classifier, which unfortunately exist. They are called transferable attacks, and they can fool absolutely everyone. Okay, so there's strong duality here on the very mild assumption, which is quite expected, because when you look at the objective function, the objective is linear in Q, linear in mu. So it's reasonable to. So for any delta, there exists a delta approximate Nash equilibrium on this, and we can the theorem used for this is a Fan's theorem. Okay, because the function is concave. In fact, it's linear. The set A is convex, M is convex, so everything turns well. So we implemented this thing, adding entropic regularizer to Q, and we published this in a paper. So in fact, by adding a simple small entropic regularization to this, you all know this, the sup transform into a softmax. So instead of trying to find the best adversary, we're now trying to sample from a distribution, which is the distribution which is proportional to the softmax of the loss. So this is exactly what we get at the end. Okay, so in fact, this trick gives us a problem which is more stable and smoother. All right. So let's skip this. This was published a few years ago, and it gave very good results. Okay. So up to now, we saw that finished mixture can outperform deterministic classifier in two-class setting against regularized adversaries, and adversaries should be regularized. And strong duality holds when using randomized classifiers. Okay, but in fact, performance of randomized classifiers has been debated, so it has been very hard, in particular in two-class, to find situations where in practice it was better than the others. And in fact, the story of adversarial defense is always the same. One guy publishes a paper saying, I found something incredible, the performance is huge, and 6 months later there's an attack which says, no, it was complete crap. It just wasn't tested against the correct attack. So it's always this thing. So in fact, stochastic defense did not have so many success up to now, and that's probably the reason for this, in particular in the two-class setting. So the question is, how much is the randomized score better than the deterministic score? All right, so let's have a look at at binary classification. Again, let's go back when you have two labels, okay? And let's note HRAND, the set of all randomized classifiers, and HDETs, a subset of these, which are deterministic. And let's note FM of H, the set of finites mixture which you can get out of H. Okay, so the finites mixture we saw up to now that the robust Fitch mixture are usually more robust, have a better risk than deterministic mixture. However, this was published in a nearest paper a few years ago. It's not the end of the story, because, so Here, the picture tells us that if we take a mixture, we will be better than a deterministic classifier under some condition. But for any classifier, randomized classifier, there exists a class of deterministic classifier which is better. Okay? So, for any deterministic classifier, we can find a mixture inside that class which is usually better, which should be lower equal. But for any randomized classifier, we can find now a deterministic classifier inside a bigger set, which is bigger, which is better. So to summarize, this is what we get. Let's start with any family of deterministic classifier, I don't know, neural networks. You can improve them by taking mixtures, for example. But once you get mixtures, you can build a new family of classifier, which is deterministic, which is even better. But then you can again take mixtures, etc., etc., etc. And this ends when Hdet is a family which is closed by unions and intersections. So take, for example, linear classifiers. Okay, linear classifiers are half planes, basically. So half planes are not closed under intersection, because if you do intersection of two half planes, you get an angle. So if you have to close the family by union intersection, you probably end up falling into Borel sets or something like that, which can be used. So randomization does not bring anything if you are in two-class setting and you're in a class of classifiers so big that it's closed on the union and intersection. Okay, but what about multi-class classifier? So multi-class classifier is a completely different topic, a completely different setting, and so here the randomization it can help a lot. So we published a paper this year in AI Stats showing lots of results on the multi-class setting. In particular, we can have a randomization gap. The randomization gap is the difference between the risk for deterministic and for randomized method, which is as close as we want to 1/2. So it's absolutely huge. So in particular, we studied this on empirical distribution because the continuous case is extremely complicated. The continuous case has an optimal transport formulation, but it's multi-marginal optimal transport with extremely complex costs. So it's tough. It's very tough. So we started to study it first on empirical distribution. Okay, so to have a look at what goes on in the multi-class setting, everything is determined by the graph and the vulnerability graph and the vulnerability hypergraph. So let's say in the multi-class setting where I have 5 points, 5 of them are of different classes. So these points can be attacked, and these balls represent the attack radius. So we see here, for example, that x3 and x4 can both be attacked and can both be attacked toward the same point. So we can build out of this a vulnerability graph where 2 points are linked if they're from different classes and if they can be attacked towards the same point. And based on this, we can also build a vulnerability hypergraph, which says the same. 3 points of different class can have an hyperedge if all of them can be attacked to a single point. All right? Okay, so the results we got out of it is a condition for a randomization, for the randomization gap to hold. Okay, so let mu be a discrete data distribution. If the randomization gap holds, then there must be one of the following situation. So the following situation is G contains an odd hole, G contains an odd anti-hole, or H, which is the hypergraph, has an uncovered click. So this might look familiar to those of you who have studied the graph theory, because this is linked to the work of Berger on perfect graphs. So we make connection on all these topics and perfect graphs. And the condition you see here, the condition under which you have a perfect graph. So all of this is related to randomized gap and duality gap inside combinatorial optimization and graphs. So we have these structural conditions. So they're not easy to interpret. So for example, here I have an odd hole. So an odd hole means that points are connected, right? The cycle is of odd length, but there's no arc. X1 is not connected to X3, X5 not connected to X5. So this is an odd hole. So because we have an odd hole, we have a randomization gap from 3,7. So the deterministic risk is 3/5, and the randomized risk is only 1/2. All right? We have an uncovered clique, for example, here, meaning that there's a clique inside the graph, which is not an hyperedge inside the hypergraph. So again, we have a gap between the risk in the randomized setting and deterministic setting. But we have here we have no structure, no such condition, so we have nothing. Okay, so our results in the multiclass setting are only beginning. Because studying just empirical distribution is a little bit disappointing in the sense that we have not much to say on continuous distributions. But we see that, first of all, this is very much linked to graph theory and combinatorial properties, which is not reassuring because it might be hard to conclude lots of things. And there's lots and lots of work to do, and in the multiclass, we really hope that we can find. So the big question we ask now is, does this structure appear in the data or not? For which I don't have any answer to give you right now. Okay, so to conclude, so we saw that there's already lots of theoretical results on adversarial and in the adversarial setting. One big question we would have is how to train adversarial attacks. How to train, under the adversarial attack, both the classifier and the attacker in a principled way. For now, it's not very clear. People use adversarial training, but it's, in my opinion, not well-founded domain. So maybe these results will have following work in this direction. And the second,
Yann,
yes.
why not using GAN?
It has been done and broken. Yeah, but yes, sorry? No. But it's natural to ask this question. It's very natural. But unfortunately, it's very easy to break it. Yeah.
So, for example, the paper you wrote, do you have also an implementation of?
Yes. No, not this one. The NeurIPS, yes, but not this one.
But this implementation, is it robust to attacks by construction?
No, not in the multiclass multiclass setting. No, it's not.
For two classes, yes.
Well, for two class, we don't need mixtures. For the multiclass setting, it's really very difficult. There's lots and lots of algorithmic technicalities to, for example, succeeding in learning diverse classifier that you can use for a mixture, because they need to be different. Otherwise, it's not a mixture. It's very difficult. And we published a paper just on this this topic this year. Okay. So another big open question is about generalization, about the convergence of the risk and the empirical risk. Also, I'm actively working on this topic. It's a very big question. Maybe we can have statistical bounds in a peg-based way, which people have been trying but not succeeding. Okay, and the last open question, on which people have been working during these, let's say, last 5 years is about certifiability. How can we build certifiable neural networks on large scale? So certifiable neural networks is neural networks which are proven to be robust to attacks. There's lots and lots of ways to do that. Okay, that's all.
Yeah, time for questions. Thank you, Yann. Fascinating topic.
Yes, so for you said that when we have two classes, we don't need randomization because we can find some class that's closed under union and intersection where it's the same. But if we want, for practical reasons, to restrain the class of classifiers into some class, for example, neural networks, that so in this case, is it still interesting to use randomization?
It is, but the gains will be small, not be huge. Well, it depends. If you're using linear models, for example, the gain might be huge, but very complex classifiers such as neural networks, they can approximate very arbitrarily well very complex functions. So they might be able to approximate a function in a function set which is closed under union and intersection. So it will be useful, but only slightly.
And for the attacker, is this like for this setting? Does it suppose that the attacker has access to the whole model, or is it sufficient for the attacker to have access only to the parameters of the model, for example?
So what can you have more than the parameters of the model?
For example, if he doesn't know the architecture of the model, he only knows...
Okay, so there's a whole family of attacks which are called black box attacks, in which the attacker has access to nothing else but just he can query the model. He can put an example at the input and take back the output. That's all. There's even ultra black box where he doesn't have anything, even not access. So he'll use other neural networks and attack them to set its attack to this one. Yes.
Thank you for the talk. My question is, does the choice of the loss function affects the robustness of the system, or
Affect the
robustness, or the results you show in case of randomization or even pure strategies?
Okay, so the true loss function in which we are interested in is the 0-1 loss. Okay, because at the end our networks make a prediction. They make the prediction cat, dog, or something else. So the attacker, he has to cross the boundary. But in fact, as I will show you later, to cross the boundary, we can make a gradient ascent with some loss functions specifically well tailored. Yes, so there are loss functions which will be used by the attacker to find a good vector of attack. But eventually, it's the 0-1 loss which counts.
A question from Teams. Do these methods extend to other problems like clustering, regression, etc.?
I don't know if in regression, in clustering, sorry, there's a well-formulated adversarial attack problem. It might be, yes, it might be, because there's an objective function, so why not try to attack it? In regression, yes, there are lots of work in regression, and so you can replace L, the 0-1 loss, by a mean square error, and the problem is looks a lot alike. So yes.
Other questions? So my question. So if you fix epsilon, somehow you would like, so if you fix your epsilon, you would like to have less possibilities of separation. You want to see, because you So it implies, in some sense, you need to have less layers or less complexity in your in the function that you're going to use, because more
So
you have.
epsilon is the budget of the attacker.
Yes, but
So why would you have less complexity?
architecture, I guess that there is a correlation between the architecture of the system and the epsilon. If you increase your epsilon, and you can attack big, you can have big attacks. This implies that your classifier cannot have, you cannot use all functions, all possible functions.
But he can.
He can.
He can, but
Optimally, no. At optimality, probably, he will not be able to.
so it would just degrade the score of all his functions.
Okay.
So what you're asking is that maybe it will degrade differently depending on the complexity of the.
I'm wondering if you want to have a robust system, you should use a less complex architecture somehow.
So
to have some.
I'd say the converse. I'd say nearly the same. I'd say it's not necessarily useful to have very complex architecture because the attacker performs some kind of smoothing. He moves the examples, so he moves. It's like moving a boundary, and it's a little bit of smoothing. So if you have very complex, it'll be smoothed out.
Okay. And why attacks should always be close to the original points?
Because they should be imperceptible to human, which try to verify them.
Okay.
But maybe if there's no human verifying it, if it's an algorithm, then the norm is different.
Okay. So here we are in problems where there is some, you can in some sense you have some authority or some that can look at the data and don't see any. Okay, I see.
Yeah.
Thank you.
Thank you.
Let's stop here, and next week we again have another game theory seminar. So it will be also about learning intersection between AI and game theory. Thank you.